Let's answer the question of section 5.1 on page 78. Question number 1. Is it exothermic or endothermic? Part A. The burning of a candle. When a candle burns, you can feel that it releases the heat and light. So this is an example of exothermic reaction. The reaction between sodium and water. If you put the sodium metal inside the water, the temperature of the water increases. The reaction between sodium and water releases the hydrogen. So the hydrogen gas produced as a result of this reaction. And the reaction is such exothermic that sometimes the hydrogen burns. So all of these are the sign that the reaction between the sodium and water is an exothermic reaction. Part C, the change from the raw egg to fried egg. So when you want to make the egg, you give the energy to the raw egg to convert it to the fried egg. So this is endothermic reactions. For converting the raw egg to the fried egg, the energy must put into the system. So this is endothermic reaction. Question number 2. Which unit is used to measure the energy changes? The unit of energy is joule, but usually we measure the energy change for chemical reaction in kilojoule. And as I have told you that we measure energy change for 1 mole of substance. So the energy change is in the unit of kilojoule per mole. Question number 3. Two sodium react with the chlorine to give 2 sodium chloride. The energy change for this reaction is minus 822.4 kilojoule. What can you conclude about the reaction? The first thing that we can conclude about the reaction is that the reaction is exothermic, and we can conclude that based on this minus sign that we have here, because the negative shows that the energy releases during this reaction. So it means by the reaction of the sodium and chlorine, 822.4 kilojoule of energy releases. Another thing that we can conclude is that the energy level of the sodium chloride, which is product, is less than the energy level of the reactant, sodium and chlorine gas. I draw the energy level diagram for this reaction. If the energy level of the reactants are here, 2 sodium and a chlorine molecule, the energy level of the NaCl, the products, are less than that one. So here we will have 2 NaCl, and this difference is the amount of energy which is given out by this reaction, which in this case is 822.4 kilojoule of energy. Question number 4. Draw an energy level diagram for A. An endothermic reaction, B. An exothermic reaction. On page 78, you have energy level diagram for an endothermic reaction. What is important here is the y-axis, the unit of that one, and what is the x-axis and the unit of that one. The y-axis is energy and the unit is kilojoule per mole, and the y-axis is the time, which can be second, minute, hour, or we can write extent of reaction or reaction progress. And one more important thing about an endothermic energy level diagram is that the energy level of the products are higher than the energy level of the reactants, and this difference is the energy which is taken in during the reaction from the surrounding. On page 77, you have energy level diagram for an exothermic reaction. You can see that the energy level of the products is less than the energy level of the reactant, and that difference is the amount of energy which is given out during the chemical reaction. And the y-axis is energy and the unit is kilojoule per mole, The x-axis is reaction progress or extent of the reaction, or we can say it's the time. Now I go to page 80 to answer the question for section 5.2. Question number 1. Two steps must take place to go from the reactant to product. What are they? We have the answer on page 79. It says in chemical reaction, bonds must first be broken, then the new bonds form. So we have two steps. In the first step, we have to break the bonds between the reactants. The second step, the new bond forms to make the products. Breaking the bonds takes in the energy, making the bond releases the energy. And here you have an example of the exothermic reaction. You have the reaction between the H2 and Cl2, and they convert to the HCl as you can see here. So what do you have on the reactant side? You have H2 and Cl2 molecules. They are converting to the HCl. So as we said, we have two steps in this reaction. The first step is that the bonds between the reactant molecules must be broken. So the bonds in the hydrogen and chlorine molecules must be broken, and this process take in the energy. We need the energy for breaking the bond. The next step, new bonds form between the hydrogen and chlorine atoms. So when you break the bonds in the reactant, we converting them to the atom. This atom rearrange and they must form the bond to become the product. Forming the bond releases the energy. So in the second step, the energy releases. The example 2 shows the endothermic reaction. The NH3, which is ammonia, is converting to its element, is converting to the H2 and N2. Again, here we have two steps. The first step is breaking the bond of the reactant. So the bonds in the ammonia must be broken. The energy must be taken in for breaking the bond. The second step, when we make the atoms, the atom rearranges and new bond forms between the atom. No, the hydrogen atoms bond together and the nitrogen atoms bond together. So this step releases the energy. So you can see in any chemical reaction, we can consider two steps. In the first step, the bond between the reactants are being broken. In the second step, after the atoms are rearranged, the new bond forms. The first step needs the energy. The second step releases the energy. Let's go to question number 2. Some reactions are endothermic. Explain why. You have the answer on page 79. If the energy taken in to break the bonds is greater than the energy released in the making bonds, the reaction is endothermic. So as we said, for breaking the bond, we need the energy. When the new bond forms, the energy releases. If the amount of energy which releases in the product side by forming the bond is less than the energy that we need for breaking the bond, the reaction is endothermic. Or in the other word, if the energy taken in to break the bonds is greater than the energy released in the making bond, the reaction is endothermic. The question may ask you why any reaction is exothermic. The answer is given here. If the energy taken in to break the bonds is less than the energy released in making the bonds, it means when the bond forms, more energy is released. The reaction is exothermic. Question number 3. Hydrogen reacts with oxygen. Draw the equation for the reaction as above with lines to show the bond. The hydrogen is diatomic molecule. It's H2 gas, and oxygen is also diatomic molecule. It's O2 gas. When they react with each other, the water forms H2O. The water can be in the gas state or water vapor, so I write H2O gas. We have to balance this equation. We have two hydrogen at the left side, two hydrogen at the right, but we have two oxygen at the left, only one oxygen at the right, so I put two here to make the oxygen two. Now I have four hydrogen on the right side, so I put two as a coefficients for the hydrogen at the left. So now everything is balanced, both hydrogen and oxygen. This is the reaction which happens between the oxygen and hydrogen. But we have to show the bonds that are between them, because in the next question it asks us, now see if you can calculate the energy change for the reaction in 3 using the bond energy table. So for using the bond energy table, we must know what are the bonds in the reactants which are being broken and what are the bonds in the products which are being formed. So I write these reactions to show the bonds that are available. The hydrogen molecule has two hydrogen atoms which are bonded to each other by the single bond. You had it in previous chapters. The oxygen has a double bond. So I have oxygen, double bond, oxygen. And it gives me 2H2O. So it gives us two water molecules. And you know, in the water molecule, there are two single bonds between the hydrogen and oxygen. So here I have the bond energy tables. So I must know what are the bonds which are being broken here. So the bonds which are broken, I have two hydrogen single bond hydrogen bond, and I have oxygen double bond oxygen. At what are the bonds which are being formed here? So bonds form. Here I have two water molecules. Each water molecule has two oxygen hydrogen bonds. So when I have two water molecules, there are four bonds between the oxygen and hydrogen which must form in the product side. Okay, so now I can use this table to find the energy which we need for breaking the bond. I have two hydrogen hydrogen. The bond energy is written here 436, so 2 times 436. And I have oxygen double bond oxygen, which is here 498. So I have only one oxygen double bond oxygen, and that is 498. So the total energy which I need for breaking the bond is 1370, and the unit is kilojoule per mole. This is energy in. I need it for breaking the bond. On the product side, I have 4 OH bond. The bond between the OH is 464 kilojoule per mole, so 4 times 464, and the total energy out is 1856 kilojoule per mole. So I found what the energy in for breaking the bond and what is the energy out by forming the bond. So I can find the energy change for this reaction. The energy change is equal energy in minus total energy out. So for this reaction, the energy in is 1370 minus 1856. So it would be negative 486 kilojoule per mole. So this minus sign shows that the reaction between the hydrogen and oxygen which result in the formation of the water is exothermic reaction. Now let's draw the energy level diagram for this reaction. The question didn't ask us to draw the energy level diagram, but I draw it because it's very important to know how we can draw the energy level diagram. So I go down to draw the energy level diagram here. On the y-axis I have energy and the unit is kilojoule per mole. I can write MOL -1. It means it is in the denominator. And on the x-axis I can write time or reaction progress or extent of the reaction. So I write reaction progress. The reaction is exothermic, so the energy level of the reactants are higher than the energy level of the products. So let me draw the energy level of the reactant here. The reactant was 2 H2 and 1 oxygen molecule. As we have calculated here, we need 1370 kilojoule of energy for breaking these bonds between the hydrogen and oxygen. So we give the energy to that to convert them to atoms. So here bonds are broken. And how much energy do we need? We need 1370 kilojoule of energy for breaking the bond. After we broke the bond, the new bond forms and it releases 1856 kilojoule per mole of energy. So it releases more energy that we used for breaking the bond. The amount of energy which releases is 1856, and you can see that the energy level of the products are less than the energy level of the reactant. So what do we have here? Here we have two water molecules, and the difference between the energy level of the reactants and products is the energy change for this reaction, which is 486. On page 82 we have the questions for section 5.3. Question number 1. A. Sketch an energy level diagram that you think shows a good fuel, a very poor fuel. B. What else do you need to think about to decide whether a substance would make a good fuel? So I answer part A of this question. On these two energy level diagram, I want to show what is the difference between the good fuel and the poor fuel. You know that the burning fuel is an exothermic reaction. So that's why the energy level of the reactants are higher than the energy level of the products for both of these two fuels. So for good fuel, if the energy level of the reactants are here, the difference between the energy level of the reactant and product is very big. So it releases a lot of energy for 1 mole. Here we have reactants, and here we have products. So you can see a lot of energy releases here. If we want to compare it with the poor fuel, let's say the energy level of the reactants are the same for both cases. The amount of energy which releases here is very small. Okay, so here is reactants, here is products. So you get more energy for burning a good fuel than burning same amount of the poor fuel, and the difference in energy level of the diagram is shown here. So the amount of energy which releases for good fuel is much more than the amount of energy which releases for the poor fuel. So this difference is energy given out for burning 1 mole of the fuel. Here the amount of energy which is given out is very small for the poor fuel. Part B of this question says, what else do you need to think about to decide whether a substance would make a good fuel? On page 81, properties of the good fuel is written. The first one we have talked in part A. So how much energy is given out for burning the fuel? If the more energy is given out, that fuel is better. Also, we have to consider if the fuel cause pollution or not. Some fuel make the pollution in the environment, so that is not good fuel. If a fuel doesn't make a pollution, that would be good feature for that one. Also, we have to consider if the fuel is easily available or not. So for example, in the oily country, the fossil fuel can be considered a good fuel because it's easily available and it's cheap. But in the countries which they don't have the oil, the fossil fuels is not a good option. The next feature which makes a good fuel is if it's safe to store and transport. If a fuel is safe to store and transport, that would be a good fuel. And also, what is important is the cost. How much is the fuel? If the fuel is cheaper, that would be a good option for that fuel. Question number 2. Look at the table above. From all the information given, which of the three fuels do you think is best? Explain. Okay, so let's look at this table that we have here. So this table shows three fuels: natural gas or methane, ethanol, and hydrogen. You can see by the burning the natural gas, the product is carbon dioxide, which is one of the gases which cause global warming. And the amount of energy which releases per gram of the fuel is 55 kilojoule. The next fuel is ethanol. It also produces the carbon dioxide, but the amount of energy which releases by burning 1 gram of that one is more, is 86 kilojoule. The third one is the hydrogen. By burning the hydrogen, it only produces the water, and the amount of energy which releases is 183 kilojoule per mole, or 183 kilojoule per gram of the hydrogen. So if we want to only consider the information which is given in this table, we can see that the hydrogen is better option as a fuel because it produces more energy per gram of the fuel, and it also only produces the water. It doesn't make the pollution. So the hydrogen is better option if we only consider the information which is given in this table. But if we want to consider the other information that we have, the hydrogen may not be a good option. The hydrogen is much more expensive than ethanol and natural gas, and the hydrogen is not a safe fuel. It's very difficult to store it and transport it compared to the ethanol and natural gas. And also, the hydrogen is not available. We have to make the hydrogen by the different processes. So all of these is a bad point or disadvantages of the hydrogen. So depends where you are, how much the cost of each one of them, if they can make the pollution or not. You can have or you can choose different options for fuel. But based on the information which is given in this table, the hydrogen is the best option. And the last question, question number 3, the fuel butane C4H10 burns to give the same product as methane, means carbon dioxide and water. Write a balance equation for its combustion. So you had the balancing of burning hydrocarbon before. So one more time, I answered this question here. Butane is C4H10. It's a gas. Burning or combustion means the reaction with oxygen. And as the question says, it produces the same product as burning CH4, the methane. The products are carbon dioxide, which is gas, and also water vapor, H2O gas. If you remember, we said for balancing the burning of the hydrocarbon, we start with balancing the carbon, then hydrogen, and in the last step, oxygen, based on the alphabet priority. I have 4 carbon here at the left side, so on the right side, I must put 4 for the carbon. Now let's go for the hydrogen. On the left side, I have 10 hydrogens. So I have to put 5 here. 5 times 2 becomes 10. Now let's go for balancing of the oxygen. How much oxygen do we have at the right side? 4 times 2. We have 8 here. 5 times 1. 5 there. So totally we have 13 oxygen at the right side. At the left side also we must have 13 oxygens. So I need to put 13 over 2 as a coefficient for the oxygen. If we multiply it by these 2 that we have here, it becomes 13. So this equation is no balance, but as you know, we cannot have fraction or decimal as a coefficient. So that's why I multiply the whole equation by 2. If I multiply the whole equation by 2, the balance equation would be 2C4H10 plus 13O2. It gives us 8CO2 and 10 H2O. So these two is multiplied by all of the coefficients. So the balanced equation is 2, 13, 8, 10. And this is the balanced equation for the burning of butane.